So we'll start the session at 6:10. Maybe let in 1 or 2 minutes people join. We'll start. Else we'll start like that. Okay, so we'll start the session. I'll share the screen first. So for better bandwidth, I'll switch off my video so that, yeah, I hope the screen is visible. Okay, so let's start this today's session. Okay, so today we'll be discussing about the lectures that you have gone through in week 3, and we'll be solving some assignment questions very related to that you have studied in this week. Okay, so before starting, I'm Balram Shah. I'm the PMRF TA for this course, that is Watershed Hydrology, by the Department of Agricultural Engineering in IIT Kharagpur by Professor Rajendra Singh. So I'm a PhD scholar at Interdisciplinary Center for Water Research at Indian Institute of Science, Bangalore. Okay, so let's start kind of summary. Okay, so before moving on to the questions or assignment questions, as we know that we are studying the watershed hydrology, right? So in this, we start with the very basics of hydrological cycle, right? So we'll start from here only. Before that, in the last 2 weeks, what we have discussed about, sorry, okay. So in the So in the last week or last 2 weeks, in week 1 and week 2, what we have gone through is what is hydrology, why we are studying watershed hydrology, the definition of hydrology, and the main fundamental thing which we study in hydrology is the distribution and how the water occur in the water cycle and the atmosphere and all, the circulation of water and all, right? So the basic thing that we need in watershed hydrology is the hydrological cycle. So we have started from the main where from we start is the precipitation, the main hydrological component. Then we have studied like what is precipitation, how precipitation is estimated or measured, then how we can use that precipitation data, what are the applications of precipitation data, and so on. Then in week 2 we have studied about other components, or if we say in 2 words, that is hydrological abstractions or hydrological losses. So we have studied about interception, we have studied about depression storage, then we have studied about infiltration, then evaporation, transpiration, or we say it as evapotranspiration, how to measure, how to estimate, what are the measurement instruments and all, right? And how, where we can apply all those. So next comes the stream flow. So in this week, the main focus is on the stream flow measurement. What are the stream flow processes? What are the stream? How we can measure the stream flow? and then how we can estimate the stream flow, and then uh, some of the applications of those, or how we can use that in hydrology, right? Okay, so with that, I'll share the screen again. So I hope you can see the screen. Okay, so I hope you can see the screen, right? There is a problem in the network. So there is some issue with the code. Okay, we'll see that later. Okay, I hope you can see the screen, right? Okay, so we'll start with here. There is some lag in the. Can you guys see the screen? Can anyone respond? And if yes, what you can see in the screen? Okay, yeah, now I think it's fine. Okay, so today we'll be discussing about the stream flow, right? So we have discussed what is stream flow. There is some issue this time. Okay, I hope it's fine. Okay, so before that, the first question is what is stream flow, right? So stream flow refers to the this we have studied earlier also, that volume of water passing through a fixed location on a river, or let's say stream, in a unit of time, right? So here, if you see in the hydrological cycle, you can see these all we have studied: evaporation and transpiration, then condensation, then precipitation, infiltration and percolation. These all we have studied earlier, right? Now you can see the main process, or the most visible component of the hydrological cycle, is the stream flow. So here you can see whatever precipitation is coming, it can be, so the process that are involved in stream flow are, so if you see the stream flow, then stream flow can be written as the total of the channel precipitation. So what is channel precipitation? Channel precipitation means any precipitation that is happening only in the channel or the river or stream. So only that, if you consider, that is considered as channel precipitation. Next we have surface runoff. And then we have the base flow. So the surface runoff is one of the main important component of hydrological cycle, and then we have base flow, which is also one of the important component. Okay, so we'll discuss this first. Sorry. Yeah. Some lag. Okay. So we'll study the process that are involved in streamflow, right? So we have studied just now. We have seen that streamflow can be written as the summation of channel precipitation, then surface runoff, and the base flow. Again, this surface runoff is one of the important components. So we know what is surface runoff. Surface runoff is a portion of precipitation that flows over the ground surface. So surface. So what is the kind of difference between surface runoff, stream flow? Stream flow is the only water or flow which is happening in the channel section or the or river or stream, whichever you consider. So whatever inflow is coming into the stream or into the river, that flow in that channel or stream or river is called as a stream flow. Whereas this surface runoff is the portion of the precipitation that flows over the ground surface, and this ultimately reaches to the streams or lakes or rivers or any other water bodies. Okay, so infiltration is another subject. So infiltration we have studied in the last semester, last week, right? So infiltration also, it will reach to the ground level, groundwater table, and then it will reach as the base flow. Okay, so this surface runoff includes overland flow and the rapid inflow or rapid interflow, we say. Okay, then I also talked about that stream flow is not only surface runoff and channel precipitation, but it is also, I don't know why this is having a problem. Okay, I think now it's fine. Okay, and next is the base flow. Why there is a lag in this? Okay, so next is the base flow. As I mentioned, that base flow also uh, gives their inputs to the stream flow. So this, let's say, the sustained or relatively constant flow of a river or stream that comes from the slow and steady release of subsurface or the groundwater into the stream, that is called as base flow, right? So in this we can see that here you can see the blue colored, that you can see this one, right? These things, so these things are happening in the rivers or streams, let's say here also, right? So these are called stream flow. So the flow that is happening in that stream, we call that as stream flow. Okay, so there are other process also, those are involved in this stream flow. First one is interflow, rapid interflow, delayed interflow. So what is interflow? Interflow is simply the lateral movement of water within the soil profile. So this, let's say the soil layers or horizons, whatever is there, if the movement of water is happening in the lateral direction within the soil profile, then we call that as interflow. Okay, and this interflow can be of two types, that is rapid interflow or delayed interflow. the water which is moving through the soil profile immediately after an intense precipitation event, we call that as rapid interflow, because it is like whenever the precipitation event is happening, the interflow is happening. That is called as rapid interflow. And next is the delayed interflow. So the delayed interflow is the gradual movement of water through the soil layers following a precipitation event. So rapid interflow is happening, and following to that, this delayed interflow happened, but it is happening for a like very extended period. Okay. Okay. So here you can see the overland flow here and the interflow here, right? And at the end, base flow is also joining, and here you can see in the river section. Why this is not coming? I hope now it's working. Yes. Okay. So I hope till this it is clear, right? Okay. So we'll move to the next process. So this surface runoff, as I mentioned, is one of the important component. Hence, the surface runoff also we'll study in a very detailed version, but we'll study that in the next week, that is week 4 or week 4 lectures. I think it is posted now. So in that we'll also study what is surface runoff, so what is surface runoff definition anyway we have studied, and how to measure that, and what are the application, why it is important, and so on. Okay. So next, what is this picture? This picture we call this as variation of processes in a precipitation event. Okay, so just now I have mentioned that when precipitation event is happening and the interflow that is happening just at that moment, we call that as rapid interflow, right? So the precipitation, this precipitation contributes to, in the hydrological cycle also we have seen that precipitation contributes to various storage and flow processes, right? So here you can see the y-axis shows the rate relative to precipitation. So rate of each of the surface storage or any of the process that is happening during a precipitation event. Now you see, just here it starts from 0%, and in the x-axis it is time since precipitation began. So at some point in the y-axis you can see a straight line, this black line you can see, this is interception and ET. So what we are saying, that when the precipitation is starting or when it is going till the end, in that case first precipitation occurs and it will go as interception and ET will take place, right? And after that only it will go to the surface. And when it reaches to the surface, the first process that starts is the infiltration, and hence this part, right? And that's why this is infiltration. After that, surface storage starts. Then we have retention and detention. We'll see this. Then we have soil moisture storage also, in which also retention and detention starts. Then we have channel flow as in overland flow, unsaturated flow, groundwater flow, and so on. Okay, and again you see at in the top we can see a small section starts from less than that of 100%, right? So channel precipitation will also be there, right? So because of that we have this small gap or straight line, right? I hope this is clear. Okay, so next what we have retention and detention. Okay, so this comes under storage. It can be in the soil moisture storage or it can be in surface storage. Surface storage as in, let's say there is some storage that is happening only at the surface, not below the surface, then that is called as surface storage. Okay, and as the water infiltrates into the soil, and the storage that is happening during that time or in that layer, we call that as soil moisture storage. Okay, so two types of storage that we have studied is retention and detention. What is retention? So retention is the storage that is held for a long period of time, right? And it is depleted by either of evaporation or infiltration. So examples can be, it can be depression storage, right? Depressions can be there, some potholes can be there, in which directly the surface water is getting stored, but it is not getting infiltrated. Oh, sorry, it can be infiltrated or it can be evaporated, right? But it is not giving it input to the stream, and that's why this is called as retention. So the water that is retained, right? Depressions or potholes, all these are retention process. Next we have detention. So what is detention? This is a short term storage. So short term storage as in before moving, what we can have small sheet of layer on the surface after when precipitation is happening, on after precipitation is happening, that storage, the short term storage that is depleted by the flow away from the storage location, that is called as detention. Okay, so the so let's say there are some water that is required to build the head for flow to start, right? So to for the flow to start taking place, there is some water which is required to build the head, and that is called here as retention. Now, as the detention storage starts filling, flow what happens to the flow? Flow away from them occurs in the form as, let's say, overland flow. Here you can see overland flow or unsaturated flow, groundwater flow. So this groundwater flow can be through the saturated aquifers which are very deep down, and all this will give its input to the channel flow, right? Okay. So overland flow as in whatever flow that is happening on the land surface we call as overland flow. Unsaturated flow, in the last week lectures we have studied that what is unsaturated zone. So the flow that is happening in that unsaturated zone or unsaturated soil near the land surface, we call that as unsaturated flow. And the flow that, as I mentioned, that is happening in the saturated aquifers deep down into the soil, we call that as groundwater flow. So all this contributes to the channel flow. Okay. Okay. So with this, we understood that what is the importance of stream flow, right? So we will study about the rainfall runoff, or here today we'll only study about the stream flow measurement process. Okay, so stream flow generation, as I mentioned, that it is because of the overland flow, groundwater flow, and subsurface flow, right? So in that, if you would have gone through the lectures, you would have came across this infiltration excess Hortenian overland flow. So in the okay, so here you can see we have in Hortenian or infiltration excess flow. So what is this infiltration excess? So we have mentioned in the last class what is infiltration rate, infiltration capacity, right? So for the first approximation, if you say for this, so let's say the first approximation, if you see, so the first approximation for Hortonian infiltration excess flow. This is called Hortonian infiltration excess flow because it is given by Horton, right? So we know that if the infiltration rate is greater than that of the infiltration capacity, but we have the definition of what is infiltration rate, infiltration capacity in the last week, then what will happen? Then, sorry, not rainfall, the runoff. The runoff will occur at the rate of I minus F, right? If the rainfall intensity is greater than that of the infiltration capacity, right? Sorry, infiltration rate. Now, this I minus F, this is called as rainfall excess or effective rainfall, also we have studied, right? For excess or effective rainfall. Okay. So then we have saturated overland flow. Okay. Other than that, we have subsurface flow and also groundwater flow, right? So one question is like, what is the difference between this infiltration excess flow and saturated overland flow, right? So here you can see the main difference that we see is, so in infiltration excess flow, what we have along with the overland flow, The depression storage also occurs, that is retention occurs. Then detention occurs, that is surface detention storage is there, right? So here what we see in infiltration, excess overland flow, excess water that cannot infiltrate into the soil surface eventually starts to flow downslope across the soil surface. So let's say if you have uh, one soil layer like this and you have a slope like this. Okay, so what will happen? Rainfall is coming, let's say. So what will happen in the Hortonian or infiltration excess flow? There will be a overland flow. Okay, and this overland flow will happen all across the slope. Okay, but in the saturation excess flow, saturation excess overland flow, we call this a saturation excess overland flow. In this, what happens? The subsurface flow returns to the surface when the capacity of the soil to transmit flow is exceeded. So what happens? So let's say it has reached the infiltration capacity. Then what will happen? The water will again come back to the surface of the soil, right? So here that water is again flow as the overland flow. So here what is happening? If I change the color in the infiltration, here we are having this is Hortonian overland excess flow, right? But in case of, it's the same slope we have and same rainfall is happening. In the case of saturated overland flow, what will happen? We'll have, so let's say water is flowing and here somewhere uh, the overland flow at the, so here at the foot of the slope will happen. Okay, so what happens? So let's say all the rainfall is happening. So all rainfall will infiltrate like this, right? And some will flow like this. But at the end here, so after it has reach the capacity of the soil, then what will happen? It will transmit the flow to the surface. Okay, so any rain falling on the saturated zone adds to the overland flow. So here also in the picture you can see, in here we have all the soil is saturated. That's why you can see the whole part is blue. But in case of here you can see there are some space here, right? We have some space here where you can see we have voids left where water can be there. So this is not fully saturated. Okay, I hope this is clear. Okay, so next we have also studied about the subsurface flow, and then uh, we have studied about the outer flow and all. So in subsurface flow, okay. So okay, before going to the subsurface flow and all, we'll see some of the questions, right? Okay. Okay, so the first question that is there is the flow towards the stream from the saturated zone beneath the ground is termed as what? Any answers? So here what we are seeing, that the flow is happening towards the stream from the saturated zone beneath the ground, and hence that is called as base flow. So correct answer will be base flow. Okay. Next question is if the rainfall intensity exceeds the infiltration rate. So let's say the rainfall intensity is I. Okay, and infiltration rate is, let's say, F. Okay, the infiltration will be equal to what? So we have given that if I is greater than F, then the infiltration will be equal to what? Right. So now infiltration rate, sorry, the rainfall intensity is more than the infiltration rate. So firstly, whatever infiltration rate is there, we have studied in the last class that it will infiltrate, all the rainfall will infiltrate. But now it is more than that of the infiltration rate. Then what will happen? It will reach the infiltration capacity, or that is I minus F. Right? It will reach to a level of infiltration capacity. Okay, so here we have not given infiltration capacity, but what is the definition for infiltration capacity? That is a maximum infiltration rate that can happen in any soil layer. We can call that as infiltration capacity, right? So the potential infiltration also is the same thing. So the correct answer will be B. Okay. Okay. So next question is surface runoff represents total water So correct answer will be what? I'll give you some time to read and then just guess and then I'll tell you the answer. Sorry. Okay. So I hope you have guessed the answer. So see, the first option is the flowing in surface channels after the rainfall. So flowing in the surface channels after the rainfall, what I mentioned, this is the channel precipitation, right? So directly whatever is flowing in the surface channels after the rainfall, we call that as channel precipitation. So this is not surface runoff. Second is obtained after deducting from the rainfall water that what has infiltrated and or evaporated from the total rainfall. So we have subtracted. So let's say whatever rainfall is happening from that, whatever is infiltrated, we are deducting that, or whatever evapotranspiration is happening, we are deducting. Then that is called as surface runoff. So this answer will be correct. Next is excluding the base flow in surface channels after the rainfall. Still, what we have both the channel precipitation and surface runoff. Uh, Next is flown or flowing through all the channels over a specific period of time. So correct answer would be B, right? Next question is which of these is not a discharge measuring structure? Okay, before moving on to this, we'll go through some concepts again. Okay, okay. So we have understood the stream flow processes, and these streams again can also be classified into different categories. Now, based on the runoff characteristics, based on the runoff characteristics of the stream, it can be classified into ephemeral river. Ephemeral rivers. What is ephemeral river? River? Any guesses? You should know this, right? And perennial river. So we know that ephemeral river is the ephemeral river or ephemeral streams are the streams which are highly variable, right? The flow pattern is highly variable, and it often uh, like the rivers or the streams are mostly dry for the extended periods. So what happens that whenever precipitation events happens, in that case the stream or the channel gets the flow, right? And in the remaining time we have it dry. So that is called as ephemeral river. Okay. Next, we have intermittent streams or intermittent rivers, right? What is intermittent rivers? From the word only, we can start understand that intermittent streams or it flows for a part of the year and may stop flowing during maybe when drought is there or something like that. So here in this intermittent streams, we have seasonal variability. So in one season, we have let's say rainfall or the flow, but in the other season, when let's say summer season is there, in that case let's say drought came and the whole channel got dried, and hence in that season we don't have any flow. So in that case what happens, that streams are called as intermittent streams, so they have relatively more consistent water flow compared to this ephemeral streams. Okay. Next is the perennial streams. So perennial, what is perennial streams? Perennial streams are the streams in which flow is consistent throughout the year. So whatever time you go in the year, you will see that there is some flow that is happening in that stream or the river, irrespective of the season. If you go to summer season, winter, or rain or monsoon season, you'll see that there is some flow that is happening into the river or the streams, right? So this one was first classification. Next classification we have is based on the flow of water. So based on the flow of water and the structure of river network, we have two classification. That is, first one is effluent stream and second one is influent stream. So from the word only you can understand that what is effluent stream. Effluent streams are the streams which receives the water from the ground. Okay, and therefore it expands downstream by becoming deeper and broader. And whereas the influent stream is like losing the stream. So stream or river that contributes its water to another body of water, such as let's say lake or larger river or ocean, that is called as influent rivers. So mostly these influent streams are found in the arid areas. Okay. So with this, we have studied the stream flow processes. Next, we'll move to the measurement of stream flow, right? So measurement of stream flow means what? Stream flow, we have studied what is stream flow. So measuring, or let's say the process of quantifying the magnitude of water that is flowing into the channel, or let's say rivers or streams, we call that as measurement of stream flow. And we have seen that it is generally in the discharge units. It can be in meter cubes per second, which can be written as cumex also, right? Or it can be written in depth unit also. So as we have studied in precipitation also, that precipitation we can mostly write it as in the depth unit, right? So this also can be written as depth unit. Just you need to for the time period that you are considering, and for the catchment area, if you divide, you'll get into the depth unit. It is also written in Q6 in US. So foot cube per second, if you consider, that is called as Q6. Okay, and the study of this, or the science of the streamflow measurement, or the study of the streamflow measurement, we call that as hydrometry. Okay. So we know why we are measuring the stream flow. The accurate measurement of the stream flow is vital for various purposes. Like if you want to do the water resources management, or let's say if you want to predict how much flood will be there, or what will be the area that will be affected by the flood, or various other hydrological research you want to do, you need this stream flow data, right? So that's why we are gonna measure this stream flow. So there are there are various methods that are there. Okay, so it can be classified into direct methods and indirect methods. Okay, direct methods are area velocity method. Then we have electromagnetic method. Then we have dilution techniques. Then we have ultrasonic methods related to sound, let's say. And indirect methods are, let's say, some hydraulic structures like welds, notches, right? Flumes and all. Okay. Then we have slope area method. So we'll study all this. So we have studied all this in all the the three lectures in this week. So we'll go through it. And we'll not go very detailed into the methods, but I'll just go so that you can get the idea like what all you have studied. So, so these direct methods and indirect methods are commonly used. Okay. So in this also, mostly what we'll see that discharge in some of the process we'll see directly we are finding the discharge. But in the direct method also, in many of the methods you'll see either you are measuring stage or the height, let's say from the some reference point or the water surface, let's say we are measuring stage, and then by some means we are getting the discharge. Or in some of the methods you'll see that we are measuring the velocity, and from velocity you know that we can write discharge as area into velocity, right? So from this we get the discharge data or stream flow data. Okay, so like that we'll see that there are several things that we have. So most commonly used is the stage discharge relationship. Okay, we call data this as rating curve. We'll see that rating curve first. So So what I said, that we mostly measure stage or velocity, and then we go to the discharge. So there are different methods in which we do the stage measurement. So how we are measuring the height from the Earth's surface? There are different methods, like manual techniques are there, or manual gauges are there, as we have seen in the precipitation measurement also. Like we have staff gauge here or wire gauge. So these are non-recording type of rain gauges. Sorry, non-recording type of staff gauges, or for stage gauges you can say. Then we have automatic stage measurement also. Okay, stage recorder. Okay, so here we can have float gauge type or bubble gauge type. We'll see this one by one. So in staff gauge, what we have one staff kind of thing. Like in precipitation, how you measure, you have a scale kind of thing. So like that, in this also, at some of the points in the channels, what we do, we put some staffs. Okay, and then using that staffs, it's kind of ruler only. We see that how much is the flow. Okay, or the stage, and from that stage we go to the discharge. Okay, so we have seen, right, that or I just mentioned that we generally use the rating curve for this. What is rating curve? Rating curve is simply the rating curve is kind of simple thing, but it is a very important thing that we have for streamflow measurement or discharge measurement, right? So we have the stage discharge relationship, and we see that, let's say it's something like this. Okay, so this is called as the rating curve. So now if you, let's say for some basin or some streams, you have the rating curve. Okay, with the stage or and the discharge measurement that you have prepared one rating curve. Now let's say if you want to define that for this stage how much will be discharged. From this, let's say for around 4 meter or some stage, how much will be the discharge. So from this rating curve you can estimate that, okay, this much discharge will happen for this much of stage. Okay, so you using this you can do the water resource management and so on, right? Okay, so staff gauge is done. Then we have wire gauge. So in wire gauge, what happens? This is also one of the non-recording type of gauge which have a drum, and it is having some graduated wire cable which is wound on the drum, and a weight is fixed at the free end of the wire, and we'll see that, like, how many rotation is done on that wire or that drum. From there we can calculate that how much is the stage or the water surface elevation. Okay, so when we measure this, so let's say we'll start, um, let's say some weight, as I mentioned, that is given to the end of the wire, right? So we'll lower that weight, and when this weight will touch the water surface and some kind of ripples will start forming in the water surface, then we'll see, okay, we'll stop it there, and we'll see that how much rotation happened, or let's say from not from the rotation, from the wire length also we can say, okay, this much of stage is there, or the water surface elevation is there, and from there again, from the rating curves, we can calculate that or estimate that how much discharge is there, right? Then we have also seen automatic or automatic flood gauge and automatic bubble gauge. We'll see that we have that here. Yes, here. So here you can see this is the automatic float gauge recorder, right? Here you can see, let's say this is the channel or the river stream, right? So here you see this is kind of automatic rain gauge. It has one monitoring station will be there, right? So like that, here also you have to put one stilling well. Okay, so this is the stilling well, right? In the stilling well, you see that there is a pen or counterweight is given. There is a float gauge or float is there. In that, in precipitation also, in during measurement of precipitation, we have seen there is one float type rain gauge, right? Like that, here also, as the water moves, the float type or this float things will move upward when the water is going up, and when it is going down it will go down, and from there we can measure that how much is the stage again, right? So it is very similar to what we have studied in the float type rain gauge. Next we have bubble gauge. So here you can see in this again. So in this, see, the main thing is we need the stilling well. This setup is very important, and hence it becomes very expensive kind of thing. So there comes the bubble gauge. So in this, what happens? The bubble gauge, you see there is one compressed gas typically. So nitrogen will be there, and it will flow through this wire, okay, or this wire, whatever, or this tube, if you say, it will be typically nitrogen, and this gas is released slowly into the stream by an orifice. So here you can see there is an orifice fixed at a specific elevation in the stream. Now what will happen? Now if the water flows up or it goes down, then what will happen? The pressure that we need to give for this orifice to create the bubble will be changing. Now we know that as you go deeper into the water, the pressure, see, this is very uh, nice thing. So from the some of the laws or some of the theories that we know about this fluid or water, we are using that and we are getting the stage. So we know that as you go deep in the water, the pressure will increase, right? And hence the pressure required at this manometer or pressure transducer or recording equipment will be more, and hence we'll understand, okay, the water depth has increased and the stage has changed, and we'll get the stage. So from all this, what we are getting? We are getting the stage. And from that rating curve that I just mentioned, which is very simple thing, but it is a very important thing, or which gives a very significant amount of information. That is the how much is the discharge or how much is the stream flow that is happening into the river or streams. Right. So the rating curve for a specific stream location is developed by, as I said, we have stream flow measurements at many different stream gauges, and from there we, so let's say if you see this, so here we have several points we'll have, and from there we can create one rating curve like this. Okay, and this is crucial because it allows the use of stream gauge, yeah, which is easily determined as we have just mentioned. Okay, so I hope till this it is clear. Right, we'll see if we have some questions on this. Okay, this is done. Next question was, which of these is not a discharge measuring structure? Okay, so we have this in later, but okay, I'll mention that these are hydraulic structure, that is weights, orifice, flumes, and all. These are structure, hydraulic structures. But current meter is used to get the velocity. We'll just see in some minutes. So for this question, which of these is not a discharge measuring structure? Correct answer will be D, that is current meter. Okay. Next question is, the rating curve is also called as, so we have just seen that rating curve is what? Stage and discharge relationship, right? Or you can see which answer will be the correct for this. Any guesses? Okay, so we have seen that elevation, sorry, discharge and depth we have seen. So answer will be B, that is discharge depth curve. Okay, so before this, we'll just see some more work. So next, after this, we have area velocity method. Okay, so as I said before, that mostly the stream flow that we are measuring will measure, before measuring that we measure stage or we measure velocity, and then using some of the things we can get to the stream flow. So stage measurement anyway we have finished. Now we'll see the velocity area method. So in area velocity method, what happens? Okay, so in area velocity method, what happens? Here it involves measuring the flow velocity. So here what we measure? We measure the flow velocity, okay, at different sections, a different section of a stream, and then we multiply that with the area. Here I say it, right? Say we can write Q as Q equals to A into V. Okay, so we'll just you should know that how you are getting to some of the equations, or what are the main thing is what are the assumptions that are there in the whatever method that we are going to use. So area velocity method, the main assumptions that is there are that it should be a steady and uniform flow. Steady flow means that the flow is constant over time, right? So with time the flow, the characteristics of the flow is not changing. Next we have uniform flow. What is uniform flow? The flow is uniform means that across the entire cross section of the stream, the flow is not changing, right? The velocity and all will not change. Now it's next. So I'll write the assumptions. Assumptions are: it should be steady flow, it should be uniform flow, it should have constant slope in the channel, whatever I'm saying, constant channel slope. Okay, and then there should be no backward. I'm not sure why it is not working properly. I hope it will come again. You guys can see the screen, but the thing is, it will not come into the video, recorded video. Ah, no, it's fine, right? Okay, so I was talking about the negligible backwater effect. So there should be no backwater effects. Okay, even if it is there, we consider that as negligible. And then we have negligible side contraction or uh, side contraction and expansion effects. Give me a minute. Some issue. Now it's fine. Okay, yeah, yeah, right. So the stream shape should be constant over the section where the measurement is taken. It should not be like it should be non-uniform or it should not be unsteady. Okay, so these are the main assumptions that are there in the area velocity method. Okay, so whenever there is a um, we this assumption is not valid, then we can't use this area velocity method. So for measuring this flow velocity, the main thing that we use is the current meter. Okay, so this current meter is an instrument for measuring the velocity of flow in a stream. Okay, so this current meter can be of, like, it can have propeller or it can have cup shaped structure. Okay, so we have just seen here the, yeah. So here you see this is the, sorry, this is the current meter. Okay, here you can see there are kind of four cups. So whenever that flow is happening, if you put it inside, what is happening, that it will move, and from there rotation we can get that how much is the stream flow velocity. So let's say the number of revolutions for this is n. It is number of revolutions. Okay, no, what is happening with this? No, I should not. Okay. Still it is coming. So based on the number of revolutions, what happens that manufacturers will give one kind of like they will give the coefficients which will have something like this relation, that is v equals to an plus v, where v is the flow velocity. Okay, and n, as I mentioned, this is the number of revolution, and this a and b are the constants or coefficients that are given by the manufacturer based on whatever instruments they have given. Okay, then other than that, we have also propeller time. So I'll show just one video. I'll share here. Um, so here you see. Okay, I'll just start from here. Yeah, so here one
Present to you
engineer is there.
the mechanical current
I'll
meter
just
and how it works. The basic parts of a current meter are: number one, the rod. The rod is
So here you can see this is a main rod, right? So here you can see there will be one more rod which will be fixed with this, right? So that you can put this inside. Now you can see here this is kind of propeller which can be vertical, it can move, right? And when this will be put into the water, based on the number of revolutions of this propeller, we can calculate that or estimate that how much will be the discharge at that section. Okay, so this is kind of propeller movement that we can see. Okay, yeah, so this much is enough for this. Okay, let's stop this here. We'll start from here. Okay, so we have all the current meters now, right? So we have studied that how the current meter looks like and all. So now with that current meter, what we can do, we can calculate the velocity, and then if you multiply the area, then we get the uh, discharge, right? So this both this propeller shaped or cup shaped. So if I write again the current meter, so current meter, that can be two types. First one is the vertical axis current meter, and second one is the horizontal axis current meter. Okay, so the horizontal axis current meter is the propeller type, and the vertical axis is the conical cups types that we have seen in the figure, right? Now the example for conical cups are price type cups or then pygmy type current meter. Those kind of current meters are having this conical cups fitted into their instrument, whereas some of the current meters like the off or the nip break or off, all these uh, are the examples for propeller type of the instrument. So mostly this current meter, both of this propeller or this should have the velocity around 0.15 to, sorry, not 4, 0.15 to 4 meter per second. Okay. These horizontal axis or the propeller type are less sensitive to vertical velocity component, and hence it is having more advantage than that of the conical cups. Okay. So next, this one is using the current meter. Next, to calculate or estimate the velocity, what we do, we see the velocity profile over a section. So let's say if you cut the section of a river, then how the velocity profile looks like. So at the bed, there will be no velocity, right? And as it moves up, it will have more velocity, and again it will reduce. So because you can see that somewhat below the surface we see highest velocity, and as you go down the velocity reduces, and at the bed there is zero velocity. Why the velocity at the surface is less than that of somewhat below the surface? Any answers? So here we see that surface velocity is lower. Why? Because due to the friction between air and water surface. Okay, because of this friction, what happens? The velocity at the surface will be less than that of somewhat below the surface. So, somewhat below the surface of the water, the velocity is maximum. Okay, so for if the streams are shallow streams, so shallow streams, let's say less than 3 meter depth. So how we calculate the or how we estimate the velocity? We take the average velocity as the velocity at zero point 0.6 time depth. So let's say if the depth of the channel section is d, then the velocity that is happening at zero point 0.6 times the depth of the flow below the water surface. So let's say here we are having 0.6 times the depth, then here whatever the velocity we have, we take that as average velocity. Okay, now let's say if there is a if there is a deep from 3 meter to 6 meter depth, any stream is there, in that case what we do, we calculate the average velocity as the average of velocity at zero point 0.2 times depth plus at 8 zero point 0.8 times of a d. Okay, so the average of that is considered as the average velocity. Okay, and in large profiles, how we are measuring this velocity? What we do, there is a big rope kind of thing, or let's say if there is any bridge kind of thing which is there between two ends or two banks of the river. And what we do, we put one rope kind of thing and we measure at different sections of the stream. We measure using the current meter that how much is the velocity, right? And from the velocity we know, from the continuity equation we can get to the discharge. Okay, for shallow streams we also use sounding rods or sounding weights, but for deep streams we use the echo depth recorder. And then uh, so what we do, so let's say you from the transducer you spray, you send some signals, or let's say it can be sound, as I mentioned that it is echo depth recorder, so it will send the sound signal, and then when it will come back from the bed we measure that, and then we can get that how much is the stage of the stream, and from there we can get and how much is the stage, and from there you can get the discharge again. Okay, so mainly we were mentioning about the area velocity method, right? Okay, so area velocity method anyway we have, sorry. Okay, so we go to the area velocity method. So this is the figure for area velocity method. So here what you can see is the we divide the sections into n minus one number of sections, right? And now you can see these are kind of equal widths section, right? So all of these are equal width, but at the end you can see the end segments. Both the end segments are different. It is kind of triangle. Okay. So now what we do, we use this formula, that is the total discharge or the total stream flow value will be equal to the summation of all the discharge value that is happening in the ith section. So I will start from, okay. Oh, yeah. So I will start from 1 to n minus 1. But as you see that at the end segments we have different kind of structure, right? So for that we'll have, it is losing connections. I don't understand. Yeah, sorry. Yeah. So at the end segments we'll have, like we can calculate the area with the similar triangle approach and all. You can just go through the lectures. I'm not going to deep how we are calculating. Right. So the area at the end segments at A1 or AN minus 1, it will be like W1 plus W2 by 2 whole square divided by 2 into W1 into y1. So it will be for a1, not for an minus 1. So simply at in place of w1, it will be wn minus 1 for del a n minus 1. Okay. For other sections, how you will and from this you can just multiply the velocity and you will get the what do you say that as the discharge. Okay, and for the remaining one, you will get del q as yi. So yi is the depth, y1, y2, y3, something like that. Okay, and you see this rectangle we consider, right? And like that, we just take the average of both the section, wi by 2 plus wi plus 1 by 2 into velocity, that is vi. Average velocity. Average velocity, as mentioned, that you can take at zero point 0.6 depth if it is shallow stream, and if it is deep stream, you can see that it will be the average of 0.2 d and 0.8 d. Okay, from there you can get the uh, total area, total discharge. That is this one. Okay, so with this, I will just do some questions again. We did do this, I guess. Okay. So the next question is average flow velocity in channels is measured at depth of. So from the water surface, we measure that if it is a shallow stream, we get it at 0.6 times the depth of the channel we take, and if it is a deep channel, then we take it as the average of 0.2 times the depth of the channel and the 0.8 times the depth of the channel. The average of that we consider as the average flow velocity for the channel, right? So the correct answer for this will be any of the A and B. If it is mentioned that if it is shallow stream, then it will be A. If it is mentioned that if it is for deep, then it will be B. Okay, but for average flow velocity, we calculate for from any of this A and B. Okay, so the correct answer will be C. Okay, see this where and all we didn't complete. Don't have any other question. Okay, so we'll move to the next part. So other than this, okay, we have questions for dilution techniques, I guess. Okay. So other than the area velocity method, we also have dilution techniques, right? We have electromagnetic method and then ultrasound method and all, right? So in dilution technique, what happens? This is also called chemical method, right? So in this, what we do, we in let's say it is mostly we use this dilution technique for small streams or streams which are having a lot of boulders or wood, where this current meter and all we can't use. That's why we use this dilution technique. Okay, so we use simple that continuity equation only. So we use the continuity principle, and we use some tracer kind of thing. Okay, some color or some chemical we use. Okay, so we use this tracer, and what we do, either there are two methods, and there can be constant rate injection method, or sorry, there can be sudden injection method. Okay, so this constant rate injection method is also called as uh, play to play to gauge method or sudden injection method. The sudden injection method is also called as slug injection method or integration method, and so on. Now what we do, we use some tracers. So we use these tracers. These tracers can be chemical. So chemicals, simple chemical are like NaCl, which we use, or sodium dichromate, right? All these things we can use, or we use uh, some radioactive element like bromine 82 and so on. Okay. Other than that, we also use some fluorescent dyes. So fluorescent dyes can be uh, it can be rhodamine, mostly the rhodamine water tracer used in this case. Okay, so what we do, we put tracer where we know the amount of tracer that we are putting at somewhere. So let's say in sudden injection, in the constant rate injection method, if you see what happens, if you see the tracer concentration. So let's say at some of the sections, so we have two sections, section 1 and section 2. So let's say you are here somewhere and you are putting the tracer here in the streams. Okay, so here you are putting the stream. So streams is flowing like this, right? So here someone is there, and you are constant at a constant rate. You are putting the tracer here, and and it will be in equilibrium and some point at section 2. So let's say you are at the section 1 and someone is at there at the section 2. Here again he will measure that how much is the concentration, and from the again from the continuity principle you can get to the, so it's like, let's say here you know the flow at section 1 q1, and let's say the total concentration, if there is some concentration of the threshold before also, it will be the total concentration, then q1 c1 let's say will be equal to q2 c2, right? So from this principle only we can get to the so let's say c2 you are measuring, c1 you know, q1 you know, from there you can tell that how much will be the q2. Okay, so in the constant rate what we see, it's simply increasing and then it becomes kind of plateau and then again it decreases. Okay, so this is like section 1 and this is section 2. So because of this plateau kind of curve, we see say it as plateau gauging or plateau gauging method. Okay, so it happens with time. And in sudden injection, what happens? If you do the same plot again with stressor concentration on the y-axis and time on the x-axis, what you see, there will be one peak kind of thing, and then again it will decrease. So here we'll have peak because sudden injection will do. Okay, and here also using the what do you say, the continuity principle, we can get to the discharge at the second section. Okay, so here in the, let's say, sudden constant rate injection method, so how we can calculate? So let's say you know the discharge at the section 1, okay, and the concentration that you are putting for that. Now let's say there is some initial concentration or some background value of the concentration is there, which is measured at time t1 at the section 2, or and we have some initial concentration also, let's say c0, then it will be like q2 into c0 will be equals to q1 plus q2 at c2. So from this you get the uh, discharge value at the second section as q1 into c1 minus c2 divided by c2 minus c0. Now let's say if there is no initial concentration, this c0 will become 0, right? So we'll see some question for this also. Okay, so in the sudden injection method, what we see, how we calculate the discharge? We calculate the discharge as mass divided by area under this curve. Okay, okay. So as I mentioned, there are electromagnetic method, okay, which follows the Faraday's law, and based on that principle, we can get to the discharge again. So what is the main advantage of the electromagnetic method? That is, it is non-intrusive. We can adapt it at any places because it is, we are not doing anything in the water stream, but we are we are not doing any mechanical thing, right? Then we have continuous monitoring we can do, and but the limitation that is there in electromagnetic method is it is only applicable for stream of around maximum width of 30 meter. Okay, so with that comes the ultrasonic method, right? So in ultrasonic method, what we do, this ultrasonic method is applicable for around 300 meter also. So in this, we send the sound pulses and the transducer will send the signals and receive the signals, and based on that, researchers or scientists have given some formulas. Like for ultrasonic method, they gave something like L square T bar tan theta into del T divided by 2 T bar square. Okay, so with this we can get the discharge, where del T is the difference between the time of sending the pulse from one point and reaching the point pulse to the bed, and then again the pulse will reflect back from the bed to the, let's say, the sensor. Okay, so the difference of time in that is called as del T. That also we can calculate using simple distance equals to speed equals to distance by time, that method. Okay, then we have ADCP, or we call it as acoustic Doppler current profiler, where we use a Doppler effect and then we can get the bathymetry survey, which produces the depth and velocity profile. It also determines that how much suspended solids or total suspended solids are present in the what do you say, in the stream. Okay, so these are some of the methods that are used. After this, I mentioned that we have hydraulic structures also, right? So we have weirs, we have weirs or notches. Just the difference is with what material it is made. Weirs, notches, then flumes, right? All these things are there. Okay, so the main advantage of hydraulic structure is over the area velocity method is that it is less influenced by the downstream conditions, or maybe if there is some channel roughness or some backwater effect. In that case, we know that we can't use the area velocity method, but we can use the hydraulic structures. So most commonly used weirs are rectangular weirs. Okay, so then we have triangular notch or triangular wear. We call this as V notch. Okay, then we have trapezoidal wear. So in rectangular wear, the formula is Q is equals to 2/3 into D. Sorry, not D. That is into H. So 2/3 into CD. CD is the coefficient of discharge. The root 2G H to the power 3 by 2 into the width of the notch. Okay, so this we use when um, B equals to B or something like that. So let's say if B is the uh, width of the notch or wear, okay, is less than that of the capital B. Capital B is the width of the channel. Then what we do, we multiply one contraction coefficient because it is getting contracted, right? Because the width is less than that of the channel width. So hence we multiply contraction coefficient also with this. Now for triangular notch, we write Q is equals to 8 by 15 CD root 2G tan theta by 2 into h to the power 5 by 2. Okay. And in trapezoidal, so trapezoidal is like, see, if you see the trapezoidal, we'll see that it is kind of, this is the rectangular part and this is the triangular part, right? So the Q will be, so if let's say if I write like QR and QT, it will be the summation of QR and QT. Okay, so here triangular is mostly, we see that it is in 90-degree angle. There are other triangular notches also which are having different angles. Okay, so in trapezoidal notch, we have one special kind of wire, we called it as Cipolliti wire. So Cipolliti wire is also a trapezoidal wire only, but the speciality is this, that it has a side slope of, so there is one fixed side slope, that is 1:4, where 1 is the horizontal thing and 4 is the vertical value. Okay, and we don't have any contraction coefficient for I mean there is no contraction, right? So we consider the contraction coefficient as 1. So if you multiply anything by 1, it will remain the same, right? So that's why the contraction coefficient for the Cipolliti wire will be 1. So no contraction coefficient is required. Okay. Okay, so with this we also have broad crested wire and all. So how this formula came and all, you should also look into this, and what are the assumptions in that. You also should look into this. You can go to any of the channel flow book or fluid mechanics books, maybe Rajiv Bhattacharya or Hanif Chaudhary or any other basic graduate level books. If you see, you can get to the derivation of the equations. Okay, so we'll directly move on to the questions first. Okay, so we'll finish only and then only directly do that. Okay. So as I mentioned that others are flumes also was there, right? So flumes are what? Flumes are like, we just form a constriction in the channel. So any constriction can be a hump. So let's say if you see the side view, the channel is going something like that, and if you put on hump kind of thing, So then the flow pattern will again change, right? It will just go like this and then again it will fall like this, something like that. So in this case you will see that subcritical event is happening, critical flow and then supercritical flow, hydrology and all. In this all you can see in the open channel flow or fluid mechanics, basic fluid mechanics books. Okay, so these flumes are also used to get to the what do you say, the discharge value, right? So what we do, either we create either we narrow the channel or we create some hump, or we can create both. Okay, so that is kind of flume. So what is the main advantage of flumes over other hydraulic structure? That is, we can get the continuous flow measurement. We can also understand that how much is the capacity to transport the sediment. There is no requirement of loss of head. Then there is a minimal risk of submergence issues and all. So because of this, mostly the flumes are used in place of this notches and all. But the thing is, in notches and wears, it is very easy to construct and all, and that's why we can directly get. Now these flumes can be partial flume. There are different kind of flumes. That is, partial flumes is there, cutthroat flumes are there. Okay, all those things. Just we'll see one picture of. So this is the partial flume. Okay. Okay. Yeah. Okay, so this is partial flume. You can see there is one converging portion where you can see the slope is leveled. Again, we have one throat portion where we have a downward slope, and then we have a diverging portion. So this is kind of one of the partial flume. Then we have cut throat, in which it is simply like this, right? So here we have converging, then we have diverging. So this is the converging portion, and then we have diverging portion, right? So we don't have any throat portion in this, and then so that's why we call this as cut throat portion, because this partial flume is very difficult to manufacture and all, and that's why this cut throat flume came into the picture. Okay, so we'll do some question and then we move to the slope area method. Okay, so this is done anyway. Next question was, so in a stability where contraction correction is considered on both sides, on one side, or contraction correction is not required, because I just now I mentioned the stability wear is a special kind of trapezoidal wear only, in which there is no contraction. Hence, the contraction correction we mentioned that we consider the correction as one. So this means even if you don't do this, so it is fine. So it will be like contraction correction is not required. Okay, the correct answer will be C. Next question is, what is the discharge in meter cube per second over a triangular notch with an angle of 90 degree when the head over the triangular notch is 0.2 meter and the discharge coefficient is 0.6. So we are given as, we have theta as 90 degree for the triangular notch. Then we have head as 0.2 meter. We have head as 0.2 meter. Then we have discharge coefficient, that is CD as 0.6, right? We have also mentioned that it is triangular notch. So we know the formula as T is equals to 8 by 15 CD into root 2G tan theta by 2 into e to the power 5 by 2, something like that, right? So just put the values, that is 8 by 15 into CD is 0.6, root 2 into 9.81 into tan 90 by 2 into, which is how much? 0.2 to the power 5 by 2. Just calculate. You will get something like 0.0254 meter cube per second. Okay, so the correct answer will be D. Okay. Next question is, the stability wear is a contracted trapezoidal wear having side slopes of, we have seen that it is like H to V should be 1:4, right? So the correct answer will be 1:4. Next question is, 25 gram per liter solution of a fluorescent tracer. So it will mention that it is a fluorescent tracer, but discharged into a stream at a constant rate. So it is a constant rate injection method, right? And the constant rate is how much? 0.00001 meter cube per second. So we have the concentration here. So C1 is equals to how much? 25 gram per liter, right? Is discharged into a stream at a constant rate of Q1 equals to 0.80001 meter cube per second. The background concentration of the dye in the stream was 0, so C naught is equals to 0. At a downstream section, the dye reached an equilibrium concentration of 5 parts per billion. So C2 is 5 ppb. Again, we know 1 ppb is 10 to the minus 3 mg per liter, right? So we'll convert this also to mg per liter. So 25 gram into 10 to the 3 gram per liter, right? Now just use that formula, that is Q2 is equals to another formula again. Sorry. Just wrote the formula, right? Q2 equals to Q1 into, and this C naught is given as 0, so we'll just write Q1 into C1 minus C2 by C2. Q2 equals to Q1 into C1 minus C2 by C2, okay? Right? So just put the values and we'll get something like 50 meter cube per second. Correct answer will be A. Just calculate this and get. So next question is, the equipment which continuously records the water level of the flowing stream is called as stage level recorder, right? The correct answer will be D. To check whether the flow in a partial flume is submerged or not, the head is measured at. So to see if it is submerged or not, what we do, we see the flow at both we see the head at both the converging section and the throat section. So answer will be both A and B. Okay. Based on the runoff characteristic of a stream, Ganga river can be classified as which type of stream? So we know Ganga river, based on the runoff characteristics, the whole year if you see in the Ganga river, it is having flow into it. So the correct answer will be perennial stream or perennial river. Okay, so correct answer will be C. Next question is, a shift in the rating curve to the right indicate means what? So let's say if we have rating curve, right, discharge and depth. So let's say we have the rating curve like this. So there is some point here. Now what it is saying, that there is a shift in the rating curve to the right, right? So it is moving something like this. So the new point is something here. Okay, so this is the new position, right? So this means what? That okay, shift in the rating curve to the right. Okay, let me see how the rating curve looks like. Okay, it's like this only, right? Or else I put the wrong option. Okay, it's like this only. Okay, so what we have, the river bed elevation, the depth, what is happening to the depth? The depth is increasing, right? So decreasing the river discharge is also increasing. No, at a given stage. So at a given stage, let's say here we have, first we have here, no, it is increasing, a change in the Streamflow measurement method. So the correct answer should be an increase in the river bed elevation. So the correct answer will be A. Sorry. Okay. So this is kind of one question. The question is, which of the following is not a dilution technique outcome, right? So these are the options. Okay, A, B, C, D, you can see, fine. So here you can see, this is kind of, these all are the dye that are being put. This is not any dye or something. This is the pollution that is happening in Yamuna river. Okay, so this is not a dilution technique. So correct answer is C. Okay, it came after. Fine. Next question is, what is the primary purpose of flow mass curve? So we have gone through the flow mass curve or flow duration curve and then slope area method. I'm not going into detail for that. So we know, okay, just to mention, Just to mention that what is flow duration curve? So flow duration curve is the is kind of cumulative probability curve. Anyway, we have done the frequency analysis in the precipitation event, right? So it is very similar to that. I mean the method. So it's a cumulative probability curve in which you see that it is in y-axis you will have the discharge, and in the x-axis you will see the probability of accidents of, let's say, any event, right? Probability of accidents and all, you know, so I'm not going to detail of that. So it is the percentage of time during which a particular discharge value is equal or exceeded. So in rainfall, what we have seen that the percentage of time during which a particular rainfall event is exceeding or equal, we take that as the probability. But here in the flow duration curve, what we'll see, the curve which will happen or in which we can get the value of the percentage of time during which one particular discharge value is equal or exceeded, that curve is called flow duration curve. And whereas what is flow mass curve? So flow mass curve is simply the curve that you will get when you plot the cumulative flow volume. So this is mostly in the cubic day, and in the x-axis it will be time. So this flow mass curve is mainly used in the supply and demand curve. Let's say if there is some dams or reservoir, how much of water should be supplied and demand based on the flow mass curve, which is also called as ripple mass diagram. Now also in many sectors we see that this flow mass curve is used, which is the conventional method to get to the how much supply there should be and how what and like that. Okay, so with this we move to the question again. Okay, so the question is, what is the primary purpose of a flow mass curve, right? So just now I mentioned that it gives the estimates of cumulative flow over the time. So the correct answer will be C. Okay. Uh, Next question is, arithmetically compute the minimum reservoir storage or Qmax days required to maintain a demand of 50 meter cube per second. So there is a constant demand of 50 meter cube per second. Now the monthly river value, the monthly river flows to the reservoir are available as follows. Okay, so these are the flow uh, that is happening into the reservoir. This is in meter cube per second. Okay, so now what we have to do? You have to this is very easy. I give some time. Okay. I think with this also is fine only. So, okay. Just do it. Let me know how much you're getting. Okay, so what we have the month, then we have the flow meter cube per second, right? Divide that March, April, so on to December. Okay, it's 94, 82, 45, 20, so on till 43. Now what we have to do? You have to do the flow mass curve, right? So here we will do arithmetical one. So we will not directly plot the graph, but we can directly get it from arithmetically. So we'll just do that. So we have the flow rate, because here you see it is in meter cube per second. So this we have flow rate. Now we will calculate the flow volume. So flow volume will be in meter cube per second in days, right? So it will be flow volume will be in cubic days. Okay. So how you will just calculate? Okay. So just cut off this first. So we have number of days in each month, right? So in January we have 31. In February, let's say you have 28 days. In March 31, in 30, and so on. And then we will have 31 days. So from there we can calculate the flow volume, right? The flow volume will be in cubic days, right? So you just multiply the number of days with the flow rate. So 94 into 31 will be something like 2914. So I have did this in my notes. I just write that 2296, 2395, 600, and so on. We get it as 1240. So now we have flow volume, right? Now what is the demand that is there? Demand is 50 meter cube per second, but it is a constant demand for the whole time. So we have the demand rate, that is 50 meter cube per second. So we'll also calculate demand volume, which will be in cubic days, right? So what will be that? So just multiply this 50 with this number of days. So 50 into 31 it will be 1550. 50 into 28 it will be 1400. And again this 1550 and 500 and so on. 1550. Just take the deficiency in this. So deficiency will be what? So this is the supply, this is the demand. What will be the deficiency? If you just subtract those values, you will get the deficiency amount, right? So you will get it as 1364, 896 minus 155 minus 900 minus 744 minus 210 and so on. So here we have 1240 and so on. And then we have minus 310. So these are the deficiency value. Again, this is in cubic days, right? So now what you will do? You will calculate the cumulative of this deficiency and cumulative of deficiency only. But in one column we'll calculate the cumulative of the negative values, and in one column we'll calculate the positive values cumulative. That is minus 155 minus 1055 minus 1799 minus 2009, and here we will have the positive value 1364, then 2260, 1240, and like that. If you just do cumulative, you will get 4890. So the maximum deficiency negative what we have will be the minimum storage value. This we know, right? So the correct answer will be B, that is 2009. Okay, I hope this is clear. Any questions? I think after this we don't have any questions. Any questions of the last weeks also? If you have, you can ask. Or if there are any doubt for today's session or in this week lectures, you can ask. Okay, so if you don't have any questions, we'll stop it here itself.